Hello and welcome. Today we're going to find out what Answers in Genesis would like us to know about rock layers. Presenting this information is Dr. Andrew Snelling, the resident geologist, who will argue that a year-long Noachian flood best explains the geological record. Not millions of years of deposition, 1 year only 4,500 years ago. I don't know about you, but I'm excited to hear what he has to say. Maybe we'll learn something new.
What do the rock layers show? Well, they show that the ocean waters flooded over the continents. How do I know that? Because there are marine fossils in rock layers covering the continents.
Well, we're off to an okay start. Remnants of marine organisms can be found in sedimentary rocks that are now exposed on dry land, so we can reasonably infer two factors at play. First, sea levels were higher than they are today. At least 66 meters worth of sea level are now stored between the Greenland and Antarctic ice sheets, but those glacial reservoirs didn't exist under warmer climates. Due to changes in seafloor spreading rate, the ocean basins weren't always as deep as they are today, and, most importantly, much of the high continental topography that we observe today is relatively young. The Colorado Plateau, the Alps, the Himalayan Range, and many other terrains were near sea level at the end of the Mesozoic some 66 million years ago. Today's continents are uniquely exposed. That being said, tectonic forces have a way of moving rocks around, and finding marine fossils in a location today doesn't mean that specific part of the continent was submerged. Convergence and crustal shortening leads to a buckling of the Earth's surface and can thrust marine deposits onto land. The Himalayas are a great example of this because they formed from the closing of an ancient ocean basin. In fact, there is a transition from marine to coastal terrestrial environments prior to uplift of what would become the world's highest range. But similar to a way a rug shortens as you push it from either side, this continental collision reduced the horizontal extents of India and Asia by more than 2,000 kilometers. Much of it subducted below Asia, and the rest stacked vertically by thrusting blocks of solid rock on top of each other through faulting. By the way, when geologists speak of flooding the continents, we are referring to sea level rise and tectonic movements that take place over millions of years or longer. It's not a catastrophic event, and I don't say that because we're biased against reading catastrophes from the rocks. We aren't, and we love to find evidence of catastrophes. However, the sedimentary structures in these marine deposits are entirely inconsistent with rapid deposition, and their fossils are indicative of local ecologies and environments similar to what we observe in the oceans today.
That's right. Marine fossils. Wouldn't you expect if they were marine that creatures lived in the ocean, they'd buried in the ocean? Well, why are they buried up on the continents? They had to get transported, lifted up by the floodwaters and dumped up on the continents.
Whoa, wait a second. Does Snelling not understand how much of marine life actually lives on the continents? Or is he trying to pull a fast one on his audience? Nearly all of the sedimentary rocks found on land that contain marine fossils were formed in shallow water, meaning water depths less than 200 meters typically, and almost none of it more than 2,000 meters depth. In other words, those rocks didn't form in the ocean basins proper, but on continental shelves. You see all of this light blue region off of the American coastline? That's part of the continent. The entire Bahamas carbonate shelf, that's deposition of marine sediment and organisms on the continent. The Great Barrier Reef, Bass Strait, Arafura and Timor Seas, more marine deposition on the continent. From the Java Sea to the Gulf of Thailand, up to the Yellow Sea, the Sea of Okhotsk, and the Bering Strait, you guessed it, more examples of marine sediments and marine fossils accumulating on the continent. The Arctic shelves of Russia and Canada, the North Sea, the Black Sea, Adriatic and Aegean Seas, and the Persian Gulf. The list goes on and on. That's tens of thousands of kilometers of coastline where marine sediments and fossils are forming before our eyes, in the same manner indicated by the geological record. So to act surprised that we find marine fossils on the continent is either a gross display of incompetence or shockingly insincere. And no, there is no need to invoke some catastrophic means of transport. Tectonics does a fine job of explaining the distribution of marine sediments. All of them are associated with ancient coastlines, continental shelves, or epiric seas like those now surrounding Europe.
And wouldn't you and I expect to find widespread, rapidly deposited rock layers because the flood was a global and it went all around the Earth? Yes.
Oh good, we can agree on this vital point. You, meaning flood geologists, would expect to find rapidly deposited layers all around the Earth. But since we find none, apart from rare tsunami deposits or debris flows within submarine canyons, your hypothesis is thoroughly falsified. And I don't mean that as an exaggeration. That's it. Flood geology is done, falsified by the total lack of corroboration for this fundamental prediction. We took it seriously as a scientific hypothesis, but it is contradicted by the preponderance of geological observations. There's really no need to go any further because Snelling has already undermined his position. Of course, we can't stop there because A, it's too much fun, and B, he's going to try and convince the audience anyways that his prediction is corroborated by observations.
We find rock layers that can be traced all the way across continents and even between continents.
Well, yes, and that's what the principle of actualism would lead us to expect. Preserved sedimentation and similar rock types across continents and even between continents due to the connectedness of the extent of shelf environments.
Let me give you examples. The Tapete Sandstone at the bottom of the Grand Canyon. It's the first layer of the flood. It sits on that erosion surface that marks the beginning of the flood.
Okay, I have to point out here, Snelling just called the Tapete Sandstone the first layer of the flood, casually ignoring up to 4,000 meters of sedimentary strata below the Tapete Sandstone. Are we to believe that 4,000 meters of rock formed without the aid of a global flood, and it did so in less than 2,000 years between creation and the flood, according to their timeline? We're not going to just let this go because it renders his reasoning incoherent. Every argument he makes for a global flood on the basis of rock layers that are Cambrian or younger will also apply to the Proterozoic aged rocks that underlie the Tapete Sandstone. Let's keep score. That's one each for now.
That's the view from the south rim of the Grand Canyon, that little cliff at the bottom there sitting on top of an erosion surface. Let's look at it a little bit more closely.
At the base of the Grand Canyon, there is an angular unconformity between the tilted Proterozoic rocks of the Grand Canyon supergroup and the near horizontal Paleozoic rocks. This boundary is termed the Great Unconformity, and it represents a widespread erosional surface that created a few 100-million-year gap in the regional rock record. For Snelling, it is prima facie evidence for the beginning of the flood, but that explanation makes little sense. This erosional surface is far too flat to have been carved by violent floodwaters, and it lacks the topographic markers associated with outburst floods. The Tapete Sandstone is dated to the Lower Cambrian, a little over 500 million years old. So let's brainstorm a little. Is there any geologic event preceding the Cambrian that could explain a widespread erosional surface? Maybe some force in nature that could potentially bulldoze entire continents? Something we observe today, perhaps, but on an even larger scale? Ah, yes, glaciers. Continental ice sheets act as nature's bulldozers and create unconformities like nobody's business. Apparently, ice is pretty freaking heavy when you stack it a mile high, and near the end of the Proterozoic, we find widespread and multiple lines of evidence for what are termed the snowball Earth events, two major glaciations that reached down to the tropics and nearly left Earth a permanently frozen state. It also removed between 2 to 5 kilometers of rock from the surface, leaving it relatively flat. Ice, not water, separates the major sedimentary units in the Grand Canyon. For those keeping score, if the erosional surface at the base of the Tapete Sandstone marks the onset of global flooding, then what about the erosional surface between the crystalline basement and the Grand Canyon supergroup?
We can study its characteristics. You know what? We can trace that sandstone in outcrop and in drill holes all the way across North America.
We can also trace much of the Proterozoic sediments.
Across to Greenland. You can go to Chippewa Falls in Wisconsin, and you can see exactly the same sandstone with exactly the same features, sitting on exactly the same erosion surface, sitting on the same crystalline basement. You can see it on a road cut in Missouri as well, in between. The same sandstone can be traced right across North Africa, right over to southern Israel, at Timnah. You've got the same sandstone with the same fossils, the same features, with the same erosion surface sitting on the same crystalline basement.
Exactly the same is misleading at best. These stratigraphic equivalents of the Tapete Sandstone are not exactly the same rock, and they weren't deposited at exactly the same time. Neither do they physically connect. They vary in sedimentary structures, thickness, mineralogy, fossils, and geochemistry. In other words, precisely what we'd expect, given that the source of the sand is not identical from one region to the next. Neither is the climate, geography, and ecology. Nonetheless, these formations all represent deposition in near-shore coastal environments, and their distribution corresponds to the shape of the respective coastlines at that time, which shifted over several million years as sea level fluctuated in response to tectonics and climate. In Arizona, the Tapete Sandstone is full of trough and planar crossbedding consistent with coastal wave action, and especially the migration of tidal channels carrying sediment to the sea. Herringbone cross stratification indicates two-way flows found in many coastal settings. The grain size varies from beach-type sand to granule conglomerate like you'd find in a stream channel, or silty sediments from slackwater deposition. There are also reactivation surfaces that indicate pauses in deposition, followed by brief erosion and then renewed deposition. None of this matches catastrophic or rapid deposition. Based on the range of sediment types, bedding structures, burrows from organisms living there, and the geometry of the Tapete Sandstone, the ancient geography can be reconstructed. So what is the Tapete Sandstone evidence for? Slow deposition over tectonic timescales, analogous to modern continental shelf and coastal environments.
Only a global flood would do that.
There is zero reason to expect that a global flood would lead to widespread deposition of marine sandstone over the continents, rather than washing it back into the ocean basins that separate those continents. There's even less reason to expect that sandstone to contain sedimentary structures and fossils and burrows and geochemistry consistent with nearshore environments. I mean, this claim is patently absurd.
You know, I was in Ireland nearly 3 years ago, and Killarney Castle is built on this rock here, and my eyes boggled. It's exactly the same limestone as in the Grand Canyon.
Exactly the same, like you can trace that layer from Ireland to Arizona? No. He's referring to a younger rock layer now, Carboniferous rather than Cambrian, which has the same approximate age as the Redwall limestone, but it's not exactly the same rock as the one exposed at Grand Canyon. Same age, same type of rock, similar fossils, but not the same rock unit. His audience has been misled into believing that there exist single layers of limestone that span multiple continents and cross ocean basins. And frankly, if I were an audience member who didn't know any better, I'd feel pretty confident too that a global flood could be responsible for their deposition. In case you think I'm being pedantic by focusing on his choice of wording and emphasis on the sameness of these rocks, I must reiterate that this is not a minor detail or a trivial distinction. It's fundamental to the argument that Snelling is making, yet completely unfounded, so it breaks his case. If in fact these rocks in Britain and elsewhere were part of the same unit of limestone exposed in the Grand Canyon, then we'd have reason to pursue an extraordinary and global explanation. Maybe not a catastrophic flood, but something unusual. But they're not. These rocks don't connect, not even close. All they tell us is that during the early Carboniferous periods, all of these locations were part of a continental shelf and covered by shallow seas. Unfortunately, his audience doesn't know that, and their confidence proceeds from a false premise.
The same features, the same fossils, exactly the same level. You can trace it across to England in the Yorkshire Dales, and you can, by the way, it's the same limestone in the Appalachians as well, so you got it in between, and you find the same limestone in the Himalayas. That's right, there's marine fossils near the top of Mount Everest.
Okay, class, why might we expect limestone to form in all these locations at approximately the same time? Keep in mind, limestone forms more or less in situ and only in regions with low inputs from sand, silt, and mud. It can't be transported thousands of kilometers in a giant slosh and still be limestone. Going back to our map, today we find active limestone deposition here in the Bahamas, and here off the coast of Indonesia, and here near Qatar, and throughout the Persian Gulf. All of these sites are shallow tropical seas with little to no sediment input from muddy rivers. By Snelling's logic, these could one day be considered the exact same rock with the exact same features, and therefore evidence of a global flood. But unless we're all living inside the Matrix right now, the globe is not being violently flooded. These are just multiple parts of the world that happen to have similar environments. Oh, and that Grand Canyon supergroup? It also contains limestones with stratigraphic equivalents elsewhere in the world.
By the way, this is my last example, the chalk cliffs of England. Remember we looked under the microscope, this type of limestone is made up of trillions of microscopic shellfish.
Chalk is composed of micrite and calcifying organisms called coccolithophores. The sheer volume of chalk from the Mesozoic alone contains more of such organisms than could feasibly be alive simultaneously, or even over a couple thousand-year period. So we can already discount the notion that chalk was deposited during a year-long event of any kind, but by all means, tell us more.
What I didn't tell you last time is that you can trace that limestone across to Northern Ireland, but you can also trace it across Europe to Germany, the Netherlands, Germany, Poland, all the way down to Israel, Egypt, Turkey, Kazakhstan. There's the same chalk beds as on the English Channel coast. And we've got the same chalk in the Midwest of the United States, from Alabama across to Colorado, from Nebraska to Texas.
Do you think that has anything to do with the fact that the Cretaceous configuration of Eurasia looked nothing like the modern one? Perhaps because sea level was at a record high and continental topography at record low, so that much of the continent was covered by epiric seas? Climatically, the Cretaceous was also characterized by greenhouse conditions with more than quadruple the modern carbon dioxide levels, which also led to arid, low-relief continents with far lower riverine fluxes of sand and mud that would normally shut down or inhibit limestone formation. All of these factors contributed to ideal conditions for maximal production from calcifying organisms in shallow seas and thus widespread deposition of chalk. It's the same story as with the tapetes, but different mineralogies reflecting the difference in coastal environments. Notably, these chalk beds record subtle changes in global seawater chemistry. That's how we can precisely align the timing of their formation. As an example, carbon isotope ratios track changes in ocean productivity and the carbon cycle. These 3 lines in the center show how that ratio changed through time at 3 locations in Europe, meaning if you analyze carbon in the individual chalk layers from bottom to top. The fact that we find robust trends that correlate from one part of the globe to another means that these chalk layers took many thousands of years to form at minimum. The oceans have a lot of carbon, almost 40,000 billion tons, and it takes a long time to change the isotopic ratio of the entire ocean. If these chalk layers formed during a global flood, however, this ratio would be flat, representing the mixing of sediment and formation of carbonate skeletons from the same global ocean. We have an easy way to test Snelling's conjecture, and yet again, it failed miserably. Furthermore, if you look at the detailed structure of the layers, their respective thickness, the precise mixture of fossils they contain, evidence of deep water or shallow, or even exposure to the air, then they record the local conditions of the basin along that coastline, a dynamic coastline which advanced and retreated with sea level change. There is a complex picture recorded in Cretaceous chalks, not a single slosh of floodwater.
The same chalk beds. By the way, the same chalk beds are found in southern Western Australia. That's a global scale fossil graveyard made up of all these trillions of microscopic shellfish.
As you may have guessed, no, these are not the same chalk beds. They are similar lithologies that formed around the same time, but they are not the same rock unit. Now, I'd love to imagine that Snelling's audience could pick up on the distinction on their own, because when geologists refer to a rock layer as being equivalent to one elsewhere, we generally mean that both represent the same depositional environment and time period. But recently, one of those very audience members quoted Snelling's point verbatim to me, a retired engineer no less who should know better how to check information. But he asked, "How could you explain that the same layer of chalk covers multiple continents, huh? It's a single rock unit. Without a global flood, you can't." Admittedly, I had to hear him repeat this a few times to realize he wasn't speaking like a geologist. He actually thought that Cretaceous chalk is a single layer, like a continuous blanket covering the Earth. Consequently, he was dumbfounded that I found his argument to be silly and misinformed, so he convinced himself that I must be dismissing real science. The internet is an amazing place, let me tell you.
Well, what do the scientists say about the formation of this limestone called chalk? They say the chalk beds formed over millions of years as lime grain by lime grain and tiny shell by tiny shell fell to the ocean floor. They say a fraction of an inch every 1,000 years. Oh, by the way, that's on the ocean floor. Where do we find the chalk? Up on the continent.
Chalk forms in shallow water where the ocean floor is up on the continent. Snelling has no excuse for failing intro geology here. Take for example the Austin chalk, which parallels the modern shoreline inland because it was deposited when sea level was about 200 meters higher than today. Similarly, this series of chalks through central Alabama. These are ancient nearshore environments that look nothing like you'd expect from catastrophic flooding of the entire globe.
What other fossils are buried in the chalk beds?
Let's form some competing hypotheses. What kind of fossils would you expect to find if these chalk beds were deposited in calm and shallow tropical seas? Probably other marine fossils like crinoids and mollusks. What kind would you expect if they were washed catastrophically over land? All kinds of fossils, marine and terrestrial, trees and trilobites buried together with impure carbonates from mixing of the mud and sand.
Well, if we go to the Niobrara chalk in Kansas, we find it's full of crinoids, perfectly formed crinoids that had to be catastrophically buried.
Oh, well that settles it then. You've just ruled out catastrophic deposition. And despite casually claiming otherwise, crinoids are delicate organisms. This is not how they'd be preserved if buried catastrophically. These lived and died in calm waters.
Or this fish didn't get time to digest its food.
That undigested meal may well have been the cause of death, so what's the surprise here?
You see the size of that fish? It's 12 foot long. Would you bury that a quarter of an inch every 1,000 years, a fraction of an inch every 1,000 years?
No, actually you would not. The rate that Snelling refers to is the long-term average, given by dividing the thickness by the total time. But chalk is largely reworked sediment, and the individual grains accumulate slowly because they are limited by biological productivity at the surface and nutrient availability. But these sediments are moved around and redeposited by individual events such as currents, storms, and wave action, as well as slope failure around mounds, reefs, and canyons across the carbonate shelf. In other words, the total buildup is slow, but redeposition, the kind that ends up preserving large fossils, is not. Snelling has presumed an oversimplified model of carbonate deposition, like a homogeneous stack of millimeter-scale pancakes, but that's not what we observe today or in the rock record. Most deposition takes place through somewhat rapid lateral migration of bars or progradation, meaning the sediment is carried from high points out toward the basin and accumulates somewhat horizontally until sea level rise can create more space for vertical aggradation. Then the process repeats. The study of these cycles is called sequence stratigraphy and is key to oil and gas exploration within the very sediments that Snelling is describing. The lesson here is that sedimentation rate at a specific place in time, such as when this fish was buried, is not the same as the regional sedimentation rate for the entire formation. We can see this heterogeneity in a reconstruction of the Gulf Carbonate platform off the Florida coastline, based on the sediment sequence from Miocene to present. Depositional rate is lowest on the middle slope until accumulation on the upper shelf leads to slope failures and debris flows that rework lime mud and bury things rapidly in localized layers. Snelling would not conflate the local depositional rate with that of the basin if he had taken and passed sedimentology. But we know he did because he earned his PhD, so apparently he feels comfortable lying to the audience. Lastly, let's point out the obvious. The seafloor is not solid. It's really, really soft, especially in the case of lime mud. A fish this size would not sit quietly on top of the substrate for thousands of years waiting to be buried. Rather, it would sink partially into the existing mud so that only a minor amount of reworking of the sediment could preserve it entirely.
Or in the same chalk bed, you've got pliosaur fossils and turtle fossils 10 and 12 feet long across. You've got dinosaur fossils and bird fossils in the same chalk beds.
In other words, fauna that lived in coastal settings of shallow tropical seas? By the way, these are toothed diving birds suited to hunting in the oceans. It's almost like the paleontology of a formation can reveal something about the ecosystem of the time.
How would you gradual, grain by grain, a fraction of an inch every 1,000 years, on the ocean floor, over millions of years, bury together such large sea, land and air-dwelling creatures on the continents, not on the ocean floor?
If that's still a mystery by this point, then I haven't done my job well enough, so I encourage you to share your questions in the comments. Overall, what have we learned from Snelling's examples? First, the geological record preserves a widespread erosional surface associated with the snowball Earth events. This led to formation of what's called the Great Unconformity in the Grand Canyon and elsewhere. Second, that continental shelves are marine settings, so that it is no surprise that we find marine fossils on the continents. It happens today across the globe. Third, any argument suggesting that Paleozoic rocks are flood deposits can also apply to the 4,000 meters of Proterozoic rock in the Grand Canyon supergroup. Fourth, that globally correlative deposits along ancient coastlines are consistent with the local environment, ecology, and slow sedimentation rate. And lastly, that Answers in Genesis is willing to lie to their audience to influence their beliefs, which is honestly no better than a certain serpent in the garden. So if you'd rather not be deceived about rocks, stick around, there's plenty more.